expose them to light and they turn dark. So the result was a negative image of the sky, with dark stars on a light background. But the real bonus was that a photographic plate can be exposed for hours on end. When you take in the night sky with your own eyes, once they're dark adapted, you don't see more and more stars just by looking longer. But with a photographic plate, you can do just that. You can collect and add up the light over hours on end. So a longer exposure reveals more and more stars. And more, and then some. In the 1950s, the Schmidt telescope at the Palomar Observatory was used to photograph the entire northern sky. Almost 2,000 photographic plates, each exposed for nearly an hour. A treasure trove of discovery. Photography had turned observational astronomy into a true science. Objective, measurable, and reproducible. But silver was slow. You had to be patient.
The digital revolution changed all that. Silicon replaced silver, pixels replaced grains. Even in consumer cameras, we no longer use photographic film. Instead, images are recorded on a light-sensitive chip, a charge-coupled device, or CCD for short. Professional CCDs are extremely efficient. And to make them even more sensitive, they are cooled down to well below freezing using liquid nitrogen. Almost every photon is registered. As a result, exposure times can be much shorter. What the Palomar Observatory Sky Survey achieved in an hour, a CCD can now do in a few short minutes, using a smaller telescope. The silicon revolution is far from over. Astronomers have built huge CCD cameras with hundreds of millions of pixels. And there's more to come.
The big advantage of digital images is that they're, well, digital. They're all set and ready to be worked on with computers. Astronomers use specialized software to process their observations of the sky. Stretching, or contrast enhancing, reveals the faintest features of nebulae or galaxies. Color coding enhances and brings out the structures that would otherwise be difficult to see. Moreover, by combining multiple images of the same object that were taken through different color filters, one can produce spectacular composites that blur the boundary between science and art. You too can benefit from digital astronomy. It has never been so easy to dig up and enjoy the amazing images of the cosmos. Pictures of the universe are always just a mouse click away.
Icy comets come and go, leaving scattered debris in their wake. Asteroids zip by. Distant planets orbit their mother stars, temporarily blocking part of the star's light. Supernovas explode, while elsewhere new stars are born. Pulsars flash, gamma ray bursts detonate. Black holes accrete. To keep track of these grand plays of nature, astronomers want to carry out all-sky surveys every year, or every month, or twice a week. At least that's the ambitious goal of the Large Synoptic Survey Telescope. If completed in 2015, its 3-gigapixel camera will open up a webcam window on the universe. More than fulfilling astronomers' dreams, this reflecting telescope will photograph almost the entire sky every 3 nights.
When you listen to your favorite piece of music, your ears pick up on a very wide range of frequencies, from the deepest rumblings of the bass to the very highest pitched vibrations. Now imagine your ears were only sensitive to a very limited range of frequencies. You'd miss out on most of the good stuff. But that's essentially the situations that astronomers are in. Our eyes are only sensitive to a very narrow range of light frequencies, visible light, but we are completely blind to all other forms of electromagnetic radiation. However, there are many objects in the universe that do emit radiation at other parts of the electromagnetic spectrum. For example, in the 1930s, it was discovered by accident that there are radio waves coming from the depths of space. Some of these waves have the same frequency as your favorite radio station, but they are much weaker, and of course there's nothing to listen to. In order to tune in to the radio universe, you need some sort of receiver, a radio telescope. Now, for all but the longest wavelengths, a radio telescope is just a dish, much like the main mirror of an optical telescope. But because radio waves are so much longer than visible light waves, the surface of a dish doesn't have to be nearly as smooth as the surface of a mirror. And that's the reason why it's so much easier to build a large radio telescope than it is to build a large optical telescope. Also, at radio wavelengths, it is much easier to do interferometry. That is, to increase the level of detail that can be seen by combining the light from two separate telescopes as if they were part of a single giant dish. The Very Large Array in New Mexico, for example, consists of 27 separate antennas, each measuring 25 meters across. Now, each antenna can be moved around individually, and in its most extended configuration, the virtual dish mimicked by the array measures 36 kilometers across. So what does the universe look like in the radio? Well, for a start, our sun shines very brightly at radio wavelengths. So does the center of our Milky Way galaxy. But there's more. Pulsars are very dense stellar corpses that emit radio waves only into a very narrow beam. In addition, they rotate at speeds of up to several hundred revolutions per second. So in effect, a pulsar looks like a rotating radio lighthouse. And what we see from them is a very regular and fast sequence of very short radio pulses. Hence the name. The radio source known as Cassiopeia A is in fact the remnant of a supernova that exploded in the 17th century. Centaurus A, Cygnus A, and Virgo A are all giant galaxies that pour out huge amounts of radio waves. Each galaxy is powered by a massive black hole at its center. Some of these radio galaxies and quasars are so powerful that their signals can still be detected from a distance of 10 billion light-years. And then there's the faint, relatively short wavelength radio hiss that fills the entire universe. This is known as the cosmic microwave background, and it is the echo of the Big Bang, the very afterglow of the hot beginnings of the universe.
Each and every part of the spectrum has its own story to tell. At millimeter and sub-millimeter wavelengths, astronomers study the formation of galaxies in the early universe and the origin of stars and planets in our own Milky Way. But most of this radiation is blocked by water vapor in our atmosphere. To observe it, you need to go high and dry. To Llano de Chajnator, for example. At 5 kilometers above sea level, this surrealistic plateau in northern Chile is the construction site of ALMA, the Atacama Large Millimeter Array. When completed in 2014, ALMA will be the largest astronomical observatory ever built. 64 antennas, each weighing 100 tons, will work in unison. Giant trucks will spread them out over an area as large as London to increase the detail of the image or bring them close together to provide a wider view. Each move will be made with millimeter precision.
Many objects in the universe also glow in the infrared. Discovered by William Herschel, infrared radiation is often also called heat radiation, because it is emitted by all relatively warm objects, including humans. You may be more familiar with infrared radiation than you think, because on Earth, this kind of radiation is used by night vision goggles and cameras. But to detect the faint infrared glow from distant objects, astronomers need very sensitive detectors, cooled down to just a few degrees above absolute zero in order to suppress their own heat radiation. Today, most big optical telescopes are also equipped with infrared cameras. They allow you to see right through a cosmic dust cloud, revealing the newborn stars inside, something that just cannot be seen in the optical. For example, take this optical image of the famous stellar nursery in Orion. But look how different it is when seen through the eyes of an infrared camera. Being able to see in the infrared is also very helpful when studying the most distant galaxies. The newborn stars in a young galaxy shine very brightly in the ultraviolet. But then this ultraviolet light has to travel for billions of years across the expanding universe. The expansion stretches the light waves, so that when they are received by us, they've been shifted all the way into the near-infrared.
This stylish instrument is the Magic Telescope on La Palma. It searches the sky for cosmic gamma rays, the most energetic form of radiation in nature. Lucky for us, the lethal gamma rays are blocked by the Earth's atmosphere, but they do leave behind footprints for astronomers to study. After hitting the atmosphere, they produce cascades of energetic particles. These, in turn, cause a faint glow that magic can see. And here's the Pierre Auger Observatory in Argentina. It doesn't even look like a telescope. Pierre Auger consists of 1,600 detectors, spread over 3,000 square kilometers. They catch the particle fallout of cosmic rays from distant supernovas and black holes. And what about neutrino detectors? Built in deep mines or beneath the surface of the ocean, or in the Antarctic ice? Could you call those telescopes? Well, why not? After all, they do observe the universe, even if they don't capture data from the electromagnetic spectrum. Neutrinos are elusive particles that are produced in the sun and supernova explosions. They were even produced in the Big Bang itself. Unlike other elementary particles, neutrinos can pass through regular matter, travel near the speed of light, and have no electric charge. Although these particles may be difficult to study, they are plentiful. Each second, more than 50 trillion electron neutrinos from the Sun pass through you. Finally, astronomers and physicists have joined forces to build gravitational wave detectors. These telescopes do not observe radiation or catch particles. Instead, they measure tiny ripples in the very structure of space-time, a concept predicted by Albert Einstein's theory of relativity. With a stunning variety of instruments, astronomers have opened up the full spectrum of electromagnetic radiation and have even ventured beyond. But some observations simply can't be done from the ground. The answer? Space telescopes.
The Hubble Space Telescope. It is by far the most famous telescope in history. And for good reason. Hubble has revolutionized so many fields in astronomy. By modern standards, Hubble's mirror is actually quite small. It only measures about 2.4 meters across. But its location is literally out of this world. High above the blurring effects of the atmosphere, it has an exceptionally sharp view of the universe. And what's more, Hubble can see ultraviolet and near-infrared light. This light just cannot be seen by ground-based telescopes because it is blocked by the atmosphere. Cameras and spectrographs, some as big as a telephone booth, dissect and register the light from distant cosmic shores. Just like any ground-based telescope, Hubble is upgraded from time to time. Spacewalking astronauts carry out servicing missions. Broken parts get refurbished, and older instruments get replaced with newer and state-of-the-art technology. Hubble has become the powerhouse of observational astronomy, and it has transformed our understanding of the cosmos.
With its keen eyesight, Hubble observed seasonal changes on Mars, a cometary impact on Jupiter, an edge-on view of Saturn's rings, and even the surface of tiny Pluto. It revealed the life cycle of stars, from their very birth and baby days in a nursery of dust-laden clouds of gas, all the way to their final farewell, as delicate nebulae slowly blown into space by dying stars, or as titanic supernova explosions that almost outshine their home galaxy. Deep in the Orion Nebula, Hubble even saw the breeding ground of new solar systems, dusty disks around newborn stars that may soon condense into planets. The Space Telescope studied thousands of individual stars in giant globular clusters, the oldest stellar families in the universe. And galaxies, of course. Never before had astronomers seen so much detail. Majestic spirals, absorbing dust lanes, violent collisions. Extremely long exposures of blank regions of sky even revealed thousands of faint galaxies billions of light years away. Photons that were emitted when the universe was still young. A window into the distant past, shedding new light on the ever-evolving cosmos.
Hubble is not the only telescope in space. This is NASA's Spitzer Space Telescope, launched in August 2003. In a way, it is Hubble's equivalent for the infrared. Spitzer has a mirror that is only 85 centimeters across. But the telescope is hiding behind a heat shield that protects it from the sun, and its detectors are tucked away in a dewar filled with liquid helium. Here, the detectors are cooled down to just a few degrees above absolute zero, making them very, very sensitive. Spitzer has revealed a dusty universe. Dark, opaque clouds of dust glow in the infrared when heated from within. Shockwaves from galaxy collisions sweep up dust in telltale rings and tidal features, new sites for ubiquitous star formation. Dust is also produced in the aftermath of a star's death. Spitzer found that planetary nebulae and supernova remnants are laden with dust particles, the prerequisite building blocks of future planets. At other infrared wavelengths, Spitzer can also see right through a dust cloud, revealing the stars inside hidden in their dark cores. Finally, the Space Telescope's spectrographs have studied the atmospheres of extrasolar planets, gas giants like Jupiter that race around their parent stars in just a few days. So what about X-rays and gamma rays? Well, they are completely blocked by the Earth's atmosphere, and so without space telescopes, astronomers would be totally blind to these energetic forms of radiation. X-ray and gamma-ray space telescopes reveal the hot, energetic, and violent universe of galaxy clusters, black holes, supernova explosions, and galaxy collisions. They're very hard to build though. Energetic radiation passes right through a conventional mirror. X-rays can only be focused with nested mirror shells made of pure gold. And gamma rays are studied with sophisticated pinhole cameras or stacked scintillators that give off brief flashes of normal light when struck by a gamma ray photon. In the 1990s, NASA operated the Compton Gamma Ray Observatory. At the time, it was the largest and most massive scientific satellite ever launched, a fully fledged physics lab in space. In 2008, Compton was succeeded by GLAST, the Gamma Ray Large Area Space Telescope. It will study everything in the high-energy universe, from dark matter to pulsars. Meanwhile, astronomers have two X-ray telescopes in space. NASA's Chandra X-ray Observatory and ESA's XMM Newton Observatory are both studying the hottest places in the universe.
This is what the sky looks like with X-ray vision. Extended features are clouds of gas heated to millions of degrees by shock waves in supernova remnants. The bright point sources are X-ray binaries, neutron stars or black holes that suck in matter from a companion star. This hot, infalling gas emits X-rays. Likewise, X-ray telescopes reveal supermassive black holes in the cores of distant galaxies. Matter that spirals inward gets hot enough to glow in X-rays just before it plunges into the black hole and out of sight. Hot but tenuous gas also fills the space between individual galaxies in a cluster. Sometimes this intra-cluster gas is shocked and heated even more by colliding and merging galaxy clusters. Even more exciting are gamma-ray bursts, the most energetic events in the universe. These are catastrophic terminal explosions of very massive, rapidly spinning stars. In less than a second, they release more energy than the Sun does in 10 billion years.
Hubble, Spitzer, Chandra, XMM Newton and GLAST are all versatile giants. But some space telescopes are much smaller and have much more focused missions. Take Corot, for example. This French satellite is devoted to stellar seismology and the study of extrasolar planets. Or NASA's SWIFT satellite, a combined X-ray and gamma-ray observatory designed to unravel the mysteries of gamma-ray bursts. And then there's WMAP, the Wilkinson Microwave Anisotropy Probe. In just over 2 years in space, it had already mapped the cosmic background radiation to unprecedented detail. WMAP gave cosmologists the best view yet of one of the earliest phases of the universe more than 13 billion years ago. Opening up the space frontier has been one of the most exciting developments in the history of the telescope. So what's next?
In Arizona, the first mirror has been cast for the giant Magellan telescope. This huge instrument will be built at the Las Campanas Observatory in Chile. Its 7 mirrors, each well over 8 meters across, will be arranged like the petals of a flower. And together they will capture more than 4 times the amount of light any current telescope can catch. The Californian 30-meter telescope, planned for 2015, is more like a giant version of Keck. Hundreds of individual segments make up one enormous mirror as tall as a 6-story apartment. In Europe, plans are ready for a European extremely large telescope. At 42 meters in diameter, its mirror will be as large as an Olympic swimming pool, twice the surface area of the 30-meter telescope. These future monsters, optimized for infrared observations, will all be outfitted with sensitive instruments and adaptive optics. They should reveal the very first generation of galaxies and stars in the history of the universe. Moreover, they may provide us with the first true picture of a planet in another solar system. For radio astronomers, 42 meters is peanuts. They hook up many smaller instruments to synthesize a much larger receiver. In the Netherlands, the low-frequency array, or LOFAR, is under construction. Fiber optics will connect 30,000 antennas to a central supercomputer. The novel design has no moving parts, but it can observe in 8 different directions simultaneously. LOFAR technology will probably find its way into the square-kilometer array, which is now topping the wish list of radio astronomers. The international array will be built in Australia or South Africa. Large dish antennas and small receivers will team up to provide incredibly detailed views of the radio sky. And with a total collecting area of 1 square kilometer, the new array will be by far the most sensitive radio instrument ever constructed. Evolving galaxies, powerful quasars, blinking pulsars. No single source of radio waves will be safe from the spying eyes of the square-kilometer array. The instrument will even look for possible radio signals from extraterrestrial civilizations. And what about space? Well, after its 5th and final servicing mission, the Hubble Space Telescope will be on active duty until 2013 or so. Around that time, its successor will be launched. Meet the James Webb Space Telescope, a space infrared observatory named after a former NASA administrator. Once in space, its 6.5-meter segmented mirror unfolds like a blooming flower, 7 times as sensitive as Hubble's. A large sunshade keeps the optics and the low-temperature instruments in permanent shadow, allowing them to operate near a whopping -233 degrees Celsius. The James Webb Space Telescope won't orbit the Earth. Instead, it will be parked 1.5 million kilometers from our planet, in a wide orbit around the Sun. Half a century ago, the Hale telescope on Palomar Mountain was the largest in history. Now an even bigger one will be flying into the depths of space. We can only speculate about the exciting discoveries it will make. Stay tuned.
Meanwhile, creative engineers come up with revolutionary designs for new telescopes all the time. In Canada, scientists have built a so-called liquid mirror telescope. In this kind of telescope, The starlight is reflected not by a solid mirror, but rather by the curved surface of a rotating reservoir of liquid mercury. Because of their design, Mercury telescopes can only look straight up, but their advantage is that they're relatively cheap and easy to build. Radio astronomers want to put a loafer-like array of small antennas onto the surface of the Moon, as far away as possible from terrestrial sources of interference. Who knows, one day there might even be a big optical telescope on the far side of the Moon. Using space telescopes and occulting disks, X-ray astronomers hope to improve their eyesight tremendously in the future. They may even succeed in imaging the very edge of a black hole.
One day, the telescope may answer one of the most profound questions puzzling humanity. Are we alone in the universe? We know that there are other solar systems out there. We suspect there are even planets like Earth with liquid water. But is there life? Locating such extrasolar planets proves difficult. They are often hidden from astronomers by the intense light radiated by their mother stars. Interferometers launched into the darkness of space may provide a novel answer. Right now, NASA is considering a project called the Terrestrial Planet Finder. And in Europe, scientists are designing the Darwin Array. 6 space telescopes orbit the Sun in formation. Lasers control their mutual distances to the nearest nanometer. Together they have incredible resolving power, cancelling out the light from overbearing stars, so scientists can actually see Earth-like planets around other stars. Next, astronomers must study the light reflected by the planet. It carries the spectroscopic fingerprint of the planet's atmosphere. Who knows, in 15 years' time we may detect the signatures of oxygen, methane and ozone, the signposts of life.
The universe is full of surprises. The sky never ceases to impress. No wonder that hundreds of thousands of amateur astronomers across the globe go out every clear night to marvel at the cosmos. Their telescopes are much better than the instruments used by Galileo. Their digital images even surpass the photographic images taken by professionals just a few decades ago. Astronomers' quest for cosmic understanding, their telescopic exploration of the universe, is only 400 years old. There's still a lot of uncharted territory out there.
We've come a long way since Galileo began charting the heavens with his telescope 4 centuries ago. Today, we still observe the universe with telescopes, not only from Earth, but in the limitless regions of space. The seed of humanity lies in our seemingly endless supply of ingenuity and curiosity. We have just begun answering some of the greatest questions conceived. We have charted over 300 planets around other stars in our own Milky Way and located organic molecules on planets around far-flung stars. These incredible discoveries may seem like the zenith of human exploration, but the best is undoubtedly yet to come. You too can join the discoverers. Look up and wonder.